Hi, everyone. So in this video, we're going to be talking about real zeros of polynomials. Real meaning real numbers. All right. So before I even discuss this rational zeros theorem, I want us to just kind of go back and look at that previous problem that we were talking about here. So in the previous video, and let me kind of clean this up a little bit. This was p of 1 equals 0. All right. So in this example here, all we wanted to do is show that p of 1 equals 0 is a factor, and we want to use this to completely factor our polynomial. So this is kind of like a very rough introduction into what we're doing today, okay? Now, here's the first thing. Number one, on the far left-hand side, and I'm going to write this in red just so you can see what I'm talking about. The first thing that we did here was we applied our remainder theorem, okay? And all the remainder theorem tells us is this. Let me write out the word theorem real fast. There we go. So all the remainder theorem tells us is if we have a possible number, in this case, that number is 1, and we substitute it into our polynomial, whatever the output of that polynomial is, whatever the output of that polynomial function happens to be, in this case, it's the number 0, is going to be your remainder if you were to divide, okay? Now, we found p of 1 equals 0, which is fantastic because immediately we know that x minus 1 is a factor. Now, that all goes back to even the previous section before that, which is this, which is if a polynomial, or if p is a polynomial and c is a real number, then the following are all equivalent. And really, what I'm really talking about here is just numbers 2 and 3. X equals c is a solution to the equation p of x equals 0. So in this case, it would be x equals 1 is a solution to the equation p of 1 equals 0. And if that is the case, then x minus 1 is a factor of p of x. It's just one of them, okay? There could be 4, 5, 6. It all depends on what your degree of the polynomial is. Now that we showed that p of 1 equals 0, what we did, and I'm talking about this right here, is we took that number 1, and we took our polynomial, and we just performed one part of synthetic division. We just did it once, okay? And what we found was we went from a third-degree polynomial into a second-degree polynomial, right in the middle of your screen. That's a second-degree polynomial. And that second-degree polynomial, we could easily factor that. And that is how we came up with the final result. P of x equals x to the third minus 7x plus 6 factors down into p of x equals x minus 1. That's from the remainder theorem. X minus 2 and x plus 3. And those two factors come from the fact that after synthetic division, we could factor that second-degree polynomial. Now, if you're asking yourself, okay, well, how is that any different from what we're going to be going over today? It's right here. It's in this step in the top middle of your screen. I am telling you that 1 is a 0. All I asked for in this problem, or in this example, was just to demonstrate that you understand what that means. In this section, I'm not telling you any of the zeros. What I need you to do is I need you to go through and find which numbers are zeros. And in order for us to do that, we're going to use this rational zeros theorem. Now, some people will call this the rational root theorem. If you went to the Google machine, you could type in rational root theorem, and you're going to get the same exact definition here, okay? So in case I use rational zeros theorem or rational root theorem interchangeably, just know they are the same exact thing. So what this theorem basically states, and you can read it, it's on your screen, but what it's really saying is, listen, if you got a polynomial and it has integer coefficients, then every rational zero of this polynomial is going to have this form p divided by q, where p and q are integers. And more importantly, p is going to be all the factors of the constant coefficient a sub 0, and q is going to be all the factors of the leading coefficient. So you're going to write the ratio of these two, and then you're going to tell me, here are all the possible zeros. And here's another thing you got to remember, all right? These can be positive or negative. So when you write this out, you're going to be writing plus or minus P all over plus or minus Q for all of them. Now, I know it sounds a little bit crazy, so let me show you an example here on how this works. And I'm going to have to pause the video because I'm about to sneeze. All right, sorry about that. I'm back, and I went ahead and I wrote the problem out. So we're going to let P of x equal x to the third plus 3x squared minus 4. And all we want to do for this example is just find all possible zeros, okay? So I need to go ahead and apply the rational zero theorem. So the rational zero theorem tells me to take all of the factors of my constant term and divide them by all the factors of my leading coefficient. And remember, these can be positive or negative, okay? So what I'm going to write here is this. I'm going to write plus or minus 4 all over plus or minus 2. And I want all the factors of these. So I'm going to get plus or minus 1, plus or minus 2, and plus or minus 4. Now, if you're sitting here wondering, where am I getting the plus or minus 2 from? We want the factors. We want factors of 4. Because if you look right here, and I'm going to highlight it for us. I'll use this purple color. So if you look at plus or minus 4 over 1, that is just 4. It's just an integer. That's it. It's going to be the number 4. In fact, maybe if I just kind of erase the plus or minus for now, just get rid of it. 4 over 1 is 4. So we're going to write all the factors of 4. It's just we need to include the positive and negative versions of that. Because if you think about it, negative 2 times negative 2 is positive 4. You still get 4. All right. So let me erase this and let me write it over again so it looks nice and neat. Plus or minus 4 over plus or minus 1. Now, here's another thing we got to be concerned with. We have 6 possible zeros. You have plus or minus 1, that's 2. Plus or minus 2, there's 4. And then plus or minus 4, and there's the total of 6. So we need a nice, easy way to kind of figure this out, okay? And to find the actual real zeros, we would use the remainder theorem. All right, and that's going to bring us into our next question. So real quick, before we move on, this question only asked, find all possible zeros. Here they are right here. Okay, now in WebAssign, in the box, they're going to want you to type it in as a comma selected list, or I forget the actual phrasing they use, all right? What you're going to have to write is -1, comma, -2, comma, -4, comma, +1, comma, 2, comma, 4. And I don't think they have to necessarily be in numerical order. Maybe put them in numerical order just to make yourself feel good. That for me would be a try it and see what happens. All right, but that's how they're going to want you to type in your answers. All right, in WebAssign. So make sure you're aware of that. So now the next example is just an extension of this one, which is find the real zeros to P of x equals x to the third plus 3x squared minus 4. So here's what we know. We already know from the rational zero theorem that all of our possible zeros are going to be plus or minus 1, plus or minus 2, plus or minus 4. Okay? Sorry, I'm going to scroll up. Now, this is where, if you have a calculator, it is going to help you out tremendously. I'm going to show you the first two just so you can get a feel on how to do this, okay? But then after that, I'm just going to type it in on the side and then just write down what the results are, okay? So we need to evaluate p of negative 4, p of negative 2, p of negative 1, p of 1, p of 2, and then p of 4. We have to check every single possible zero. And our goal, remember the goal here, is to find one of those zeros such that when I substitute it in, I get 0 as an output. That's the goal for this. So let me show you how I do this on a calculator. By me typing in negative 4, store an x, and then actually typing out x to the third plus 3x squared minus 4, what my calculator did was this. It said, all right, well, oops, wrong number. What my calculator said was, since you stored negative 4 in for x, and anytime I hit the x button, it's going to be negative 4, my calculator just literally took that polynomial with x equals negative 4, simplified it, and it came out to be negative 20. Okay? Now, here's what we know. Our goal is p of c equals 0. In this case, p of negative 4 equals 20. So I know p of negative 4 is not a 0 to my problem. Okay? So now I'm going to go ahead, back to the calculator. I'm going to try p of negative 2. And I'm going to type, or I'm going to write in the word. I'm going to write the number 0. And what I like to do here is put a box around it. Maybe write the word good. In other words, I know that negative 2 is one of my factors. Okay? So I'm just going to go ahead and just off to the side here, I'm going to type in everything else. So p of negative 1, when I evaluate that into my function, I get negative 2. That is not a 0. So I'm just going to go ahead and cross it out. I'm going to try p of 1 now. So 1, store an x. And when I go ahead and do that, I get 0 again. So this is good. Now remember, we have a third degree polynomial. So we are expecting to find, hopefully, 3 possible roots. So let's continue. So I get 2 store an x. Like I said, I'm doing this just off the side here on my calculator. This gives you 16. So that's no good. And then p of 4, well, p of 4 is going to be even larger than p of 2. I'll do it again just so you can verify, or just so we can verify it here. But that's going to turn out to be positive 108. And that's no good. All right. So something is definitely going great for us, but then now we've hit a roadblock. And here's the roadblock. This is a third degree polynomial that we started with. So far, and I'll highlight it for us, and I'll do this nice green color. So far, we've only found P of negative 2 equals 0 and P of 1 equals 0. In other words, even though this polynomial says we should get 3, we only found 2. And that is going to go all the way back to the definition of what we're doing. So let me scroll up real fast. This rational zeros theorem, all right, gives you all possible zeros, okay? It doesn't mean it's going to label every single one for you individually. Keyword, individually, okay? What this tells us is it gives us the possible. It's still up to us to find them all. So, scrolling back down, looking at my polynomial, P of x equals x to the third plus 3x squared minus 4. Since we only found 2 zeros, that means one of our possible zeros must have a multiplicity. All right? One of our zeros has to have a multiplicity. And that is going to lead us into our next example, which is going to be the next idea. Completely factor f of x equals, P of x equals x to the third plus 3x squared minus 4. Now, if I just gave you this problem on a test, there are no techniques that exist that you know of, meaning, using the factoring flowchart and everything. None of that stuff works for this problem. We have to be relying on what we've learned. So here's what we know, and I'm going to just review it, and then we're going to do this problem. First example, maybe I should have wrote EX there. First example was to find all possible zeros. We did that. It's highlighted in blue, plus or minus 1, plus or minus 2, plus or minus 4. Now, the second example was find the real zeros. All right? And how did we do that? We used the information from the previous example, and maybe I should have used green. We used the information from the previous example and the rational root theorem. And what we found was P of negative 2 equals 0, which was good. And then P of 1 equals 0, which was also good. Okay? This example tells me to completely factor P of x. Now, we know one of our zeros from the previous example has to have a multiplicity. So, to completely factor, we're going to use C equals negative 2 or C equals positive 1 and synthetically divide. And by doing this, this will tell me where's my multiplicity, or better yet, it will tell me what number is my multiplicity. So it doesn't matter which one you pick. I use the word or, C equals negative 2 or C equals 1. But what I'm going to do is I'm just going to choose the first one because I already know what the answer is and I want us to see how this works. So let's go ahead. Let's set this up. And you remember, be careful. Be careful. Look at the polynomial. X to the third plus 3x to the second plus 0x minus 4. You need to put that linear term in there because it's missing. Has to be in descending order. No missing terms whenever we synthetically divide. So let's write out the coefficients. 1, 3, 0, negative 4. We're going to copy down the first coefficient, and at the very end, I already know the remainder is going to be 0 because of the previous example when using the remainder theorem. So let's go ahead, let's synthetically divide. If you need to, please go back and watch the video about synthetic division because I kind of go a little bit fast and I don't write as much here. Excuse me. So negative 2 times 1 is negative 2. 3 plus negative 2 is 1. Negative 2 times 1 is negative 2. 0 plus negative 2 is negative 2. And then finally, negative 2 times negative 2 is positive 4. And negative 4 plus 4 is 0. This is fantastic. This is exactly what we would expect. But here's the thing. If we suspect c equals -2 has a multiplicity, then synthetically divide again. All right, so watch what I do here. I'm going to take -2 again, and I'm going to use my previous output. So I'm just going to copy down 1, 1, -2. And I'm hoping that this remainder right here, I'm hoping that this is going to be a 0. If it's a 0, then I know -2 has a multiplicity attached to it. If our remainder is anything other than -2, I'm sorry, I said that wrong because I was looking at the number. If our multiplicity is anything other than 0, it's not a multiplicity. So let's go ahead and let's synthetically divide. -2 times 1 is -2. 1 plus -2 is -1. And -2 times -1 is +2. Finally, -2 plus 2 is 0. So notice I synthetically divided twice with -2, which means c equals -2 has a multiplicity of 2. So my factored form p of x is going to be x minus -2 quantity squared times x minus 1. And then just to clean this up, p of x equals x plus 2 quantity squared, because you have that double negative, times x minus 1. And right there is going to be all of our factors and multiplicities written out very neatly. And here's what's also unbelievably amazing about this, okay? Watch this. This is why I fell in love with mathematics. I mean, math was always pretty fun for me, but this is where I knew it was like it. Like I knew I just loved it. All the way back up top, right here, in red, you can see me drawing the arrow. This is our original polynomial. And I'm going to write it in red directly above. It was x to the third plus 3x squared plus 0x minus 4. Okay? Then, after we synthetically divided once, here's our new answer. All right? I'm going to write it in red. This is x to the second plus x minus 2. But then we said, okay, if we suspect -2 as a multiplicity, we're going to synthetically divide again. So right here in this red arrow, sorry, I know I'm bouncing left and right. Right here, remember, that's our polynomial, x to the second plus x minus 2. All right? After synthetic division, again, here's our final result. Now, every time you synthetically divide, remember, you decrease your polynomial by 1 degree. So if you're following along, we went from x to the third to x to the second to finally x to the first minus 1. And if you set x to the first minus 1 equal to 0, and you added 1 to both sides, look at what you just found. You found the other 0. So, really what this all boils down to is if you can just find one possible 0 and get extremely lucky that it has a multiplicity and your polynomial is not like x to the 15th, you can just use a good guess, your remainder theorem, synthetic division, and you can completely factor any polynomial that exists. All right? Now, I know this was a lot, so let me go over another example where the example is going to be simple. It's going to say completely factor, but I'm going to go through every single step for us, okay? Okay, so here we go. Here's our next example, and I'm sorry if you can hear rain in the background. I have my windows open to my office. It's like the first time I can have the windows open since the fall, so I'm very excited about this. But anyways, let's get back to work. So completely factor, p of x equals x to the third plus 2x squared minus 13x plus 10. Okay. Now we do have a nice technique that we can rely on. Your book kind of goes over this, but it kind of skips something, which I think is really important. So I'm going to write it out. First, list all possible zeros. That is the rational zero theorem. Okay. Second, use the remainder theorem to find P of C equals 0. In other words, find values of C such that when you substitute it in, you get 0. That these will be your possible zeros. Okay. Step 3, synthetically divide. Okay. Now, this is step 4. If you have fewer zeros than the degree indicated, use synthetic division again to find multiplicities. Okay? And then that's it. Step 5 would be write factored form. Okay? Now, later on, there's going to be some techniques that help us to find this very quickly. Okay? Like Descartes' rule of signs, and there's another one called the upper and lower bounds. I'm going to go over Descartes' rule of signs. I'm not even going to touch the upper or lower bounds because it's really not necessary. Okay? But it's there if you want to go over it. So here we go. Here's our steps. Hopefully you have them written down, because what I'm going to do is I'm just going to go right into this problem, and I'm just going to go through every single one of these steps, not quickly, because I want you to see how this is going, but I'm going to go ahead and just do it. So here we go. We got P of X equals x to the third plus 2x squared minus 13x plus 10. Step 1. The rational zero theorem says that all my possible zeros are going to come from plus or minus the constant term divided by plus or minus the leading coefficient. Therefore, I want all the factors of just 10. So, plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. Why? 1 times 10 is 10, 2 times 5 is 10. Those are my factors, and I'm going to have plus or minuses of each of those. Okay? Now, step 2. We're going to use this remainder theorem. Okay? Now, I'm a huge fan of working smarter, not harder. Here we have 8 possible zeros. Okay, we got 8 of them. So maybe it's in your best interest to get a calculator out, or you can use something else like Excel. Let me show you. There we go. There we go. Here they are in our notes right here. Beautiful. So step 1, find all possible zeros. Step 2, use the remainder theorem. We found C equals -5, C equals 1, C equals 2. There are all my zeros. Now, remember, this is a third degree polynomial. Third degree polynomial, which means 3 zeros. Oh, I can't even spell the word zeros. I'm so excited. Now, notice I'm not using the word real zeros because in the next section, not all of our zeros are going to be real. Just know, third degree polynomial, you get 3 zeros, okay? Now, step 3 would be synthetic division. But since we found in our remainder theorem the ones that are equal to 0, we don't have to do it. We can skip. That's fantastic. Step 4, I forget what step 4 was. If you have fewer zeros in a degree indicated, use synthetic division again. Skip. We can go all the way down to step 5. P of x is going to equal, our factored form will be x minus -5 times x minus 1 times x minus 2. And just to clean this up, P of x is going to be x plus 5 times x minus 1 times x minus 2. And that is our completely factored form. So let's go ahead. Let's do another example just like this. Factor. Oops. P of x equals x to the third minus 6x to the second plus 12x minus 8. All right, now I will warn you, not all zeros are pretty. So let's see what happens here. Step 1, the rational zero theorem. So we're going to get 8 over 1 or plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. So once again, we have 8 possible zeros. So there's step 1. Step 2. Here's our remainder theorem. All right. So I'm just going to go back into Excel. I'm going to have to fix some stuff. So I'm going to use the magical powers of editing. So using the remainder theorem, we found P of 2 equals 0, but we know we have a third degree polynomial here. So this 2 has to be a multiplicity. Now we're going to have to kick in synthetic division. So put a 2. Let's set this up. Make sure descending order, no missing terms. 1, -6, 12, -8. Drop this down. Oh, what just happened there? That was weird. All right, and we're just going to go from left to right using synthetic division. 2 times 1 is 2. -6 plus 2 is 4. 2 times 4 is 8. 12 plus, oh, yeah, this is -4, my bad. So that's -8. 12 minus 8 is 4. 2 minus 4 is positive 8, and that gives us our remainder, which is fantastic. Now, this was only one synthetic division. We need to do this again and again and again until we find our 3 roots. So far, we found our first 0. Now, synthetic divide again with the number 2. So we're going to copy down 1, -4, 4. Drop down the 1. This is going to be a 0. Oh, sorry, I'm giving away the answer. This will be our remainder. So 2 times 1 is 2. -4 plus 2 is -2. 2 times -2 is -4. And 4 minus 4 is 0. So here's our second 0, which means so far it has a multiplicity of 2. And then if you wanted to, you can do this again. But remember, let me zoom out here. This was a 3rd degree polynomial. Turns out this is a 2nd degree polynomial, which means this is a 1st degree polynomial. X minus 2 equals 0. Add 2 to both sides. X equals 2. Here's our third 0. So, our completely factored form, P of X equals the quantity X minus 2 to the 3rd power. That's how we factor this problem right here. Okay? Absolutely fascinating when you really take a step back and think about how easy factoring really is. If you would have known about the rational root theorem or the rational zero theorem and synthetic division and the remainder theorem all from day one. All right, let's do another one. Okay, so here's our next problem. Step 1, we're going to write out the possible roots. So the rational root or rational zero theorem says plus or minus 3 over plus or minus 4. Uh-oh. This one's not going to be that fun because watch what happens. You get plus or minus 3 over 4. And this means that you can really have, and I hate to do this to you, but you just gotta believe me on this one. Plus or minus 3 in the numerator, okay? And then you're gonna have, well, actually, you know what? You're gonna have plus or minus 1, plus or minus 3 in the numerator, and then you're gonna have plus or minus 1, plus or minus 2, and plus or minus 4 in our denominator. See, all the other problems we had, let me scroll up here real quick. You had a 1 in your denominator, even in the previous problem. This was 4 over 1 again. It was, you still had a 1 in your denominator. Here's a situation where we don't have only a 1 in our denominator. We actually have 1 times 4 or 2 times 2. So our possible zeros are going to be plus or minus 1/4, plus or minus 1/2, plus or minus 1, plus or minus 3 over 2, plus or minus 3 over 4. Now, I know this can look a lot of confusing. All right, so let me show you how I did this. Here's plus or minus 1 in my numerator. And there's plus or minus 4. There's the 1/4, okay? Now, here in blue is the 1/2. And here in blue is going to be the plus or minus 1, just the integer, okay? I'm trying to go back here. All right, we'll just change color. Now, here's plus or minus 3. Oh, I forgot one. I'm so glad I'm doing this. Because we have 3 over 1, plus or minus. Might as well write that in while I'm sitting here. All right. Then here's the plus or minus 3 over 2. And finally, plus or minus 3 over 4. So when you look at this 2, 4, 6, 8, 10, 12, you have 12 possible roots. All right. So that is why if you got a calculator or if you're using like Excel or something like that, it makes your life so much easier. Okay. So step 2, do this remainder theorem again. So give me 1 second. I'm going to set everything up for us. All right. Now, one of the most I went ahead and wrote them down for us. All right. So step 3 would be that synthetic division. Actually, this is like step 3 and 4. That all deals with synthetic division and multiplicities. But if you look here, remember, we have a 3rd degree polynomial. And we found our 3 roots, or our 3 zeros. Sorry, there goes me slipping up again. We found our 3 zeros, okay? So I don't have to do steps 3 and 4 because I know these are my zeros already. So step 5, which is our final step. All right, we're going to write them out in the form they're in now, and then we're going to simplify it a little bit. So P of x equals x minus negative 3 over 2, x minus 1/2, and x minus 1. Now, WebAssign, knowing them, they're probably going to want the answers like this. 2x plus 3, 2x minus 1, and x minus 1. So before I even go on to the next problem, because I do have one more example that I'd like to do, I'm going to go through and show you how I did this. First, this is really x plus 3 over 2. Now, if I were just to take this and multiply it by 2, that gives me 2x plus 3. That is how I got 2x plus 3. Okay? Second, I write it over here. This is x minus 1/2. However, if I just multiply this by 2, that gives me 2x minus 1, and that's how I got 2x minus 1. So here's the proper answer. P of x equals 2x plus 3 times the quantity 2x minus 1 times the quantity x minus 1. All right, so here's our last example. And this one is going to be by far the ugliest answer we're going to get. So P of x, let me write directions real quick. Factor. P of x equals x to the fourth minus 6x to the third plus 4x squared plus 15x plus 4. All right. Now, I'm telling you, this is going to be ugly, so just kind of bear with me on this one. Step 1, rational zero theorem, plus or minus 4 over plus or minus 1. So the only possible roots we're going to have are plus or minus 1, plus or minus 2, and plus or minus 4. So that is great for us, okay? Step 2. This is going to be our remainder theorem. All right. And I'm going to save us a lot of work here. These zeros are going to be -1 and 4. Okay. So there are the possible zeros. Okay. Now notice, fourth degree polynomial, yet according to the remainder theorem, there's only 2 of them. And I'm telling you what they are, but by all means, verify by using the remainder theorem and make sure you test every single one of them. Step 3. Now, we know this is a fourth degree polynomial. However, we only have 2 terms. So we're going to have to use synthetic division and see what happens. Okay. So I'm going to do -1 first. I'm going to write out the coefficients here. So we have a 1, -6, 4, 15, and 4. We know this is going to be our remainder. And we also know that it's going to be 0 because -1 did work for us when we used the remainder theorem. So now it's just a matter of doing this. So -1 times 1 is -1. -6 plus -1 is -7. Then you get -1 times -7 is 7. 4 plus 7 is 11. -1 times 11 is -11. 15 plus -11 is 4. -1 times 4 is -4, and you get 0. So remember, this is a fourth degree polynomial. This last row is a third degree polynomial. So we are suspecting maybe there's a multiplicity. So I'm going to do -1 again. So I choose 1, -7, 11, and 4. That's our third degree polynomial after 1 successful synthetic division. Now, I can't write a 0 in that little box because I don't know if this has a multiplicity or not. I'm hoping it does, but maybe it doesn't. -1 times 1 is -1. Here you're going to get -8. -1 times -8 is +8. And get -15. I know my math is correct. I know -15 is not 0. This does not equal 0. So -1 does not have a multiplicity there. So let's go ahead. Let's try 4. And what's nice is since we already established that -1 is a 0, we don't have to redo all this synthetic division. We're just going to start with that third degree polynomial, +1, -7, 11, and 4. All right. So yeah, you don't have to restart the whole process. It's just -1 does not have a multiplicity. So use the other root. 4 times 1 is 4. -7 plus 4 is -3. 4 times -3 is -12. 11 plus -12 is -1. 4 times -1 is -4. And -4 plus 4 is 0. That is good. But all this did was verify 4 is a root. I need to do it again to see if there is a multiplicity here. Okay, I need to do it again. So this was a third degree polynomial. This is a second degree polynomial. So let's see if there's a multiplicity again. 1, -3, -1. Drop down the 1, and we're going to do this again. 4 times 1 is 4. -3 plus 4 is -1. I'm sorry, +1. 1 times 4 is 4. Uh-oh. We get 3. And that is not 0. So here's what we know. -4 does not have a multiplicity. So let me zoom out here so we can see everything on the board right now. First, we know -1, definitely a root. We also know 4, definitely a root. We also synthetically divided with them. So here's what ends up happening here. Let me highlight it for us. What we did is we took -1, synthetically divided our polynomial, and we got this third degree polynomial. Check. Then we took that result, highlighted in blue, and we synthetically divided 4 by it to get this result, which is a second degree polynomial. Now, before I give you like the, hey, here's what happened, I want us to go all the way back to the definition. I'm going to come all the way back up here. Just going to erase some stuff real quick. This rational zeros theorem gives you integer coefficients, gives you integer possible roots, but not all roots have to be integers. I mean, think about it. On a number line, between 0 and 1, actually, let me be more specific. How about between 0 and 2? You got the square root of 2, which is a 0. It is. It's just not an integer 0. It's not pretty, but it's still a 0 because it's on that x-axis. So what we have to do is come all the way back to our problem and note that the very last row, and I'm going to get my red marker out, a big red marker, this right here is a second degree polynomial, which means x squared minus 3x minus 1 equals 0. What you're going to have to do here is use your quadratic formula to find the other roots, and they are ugly. But let me show you what they are. So a equals 1, b equals -3, c equals -1. So you get x equals, make sure you're using parentheses when you make your substitutions. So I'm just writing this out as fast as I can because I know this video has already been unbelievably long. Okay. So x equals 3 plus or minus the square root of 9 minus 4 all over 2. Oh, I'm sorry. I got a mistake here. This is -1. So this is 9 plus 4. X equals, remember, sorry, I went really fast with that mistake. C is -1, so make sure you make that correction. So x equals 3 plus or minus the square root of 13 all over 2. And here, x equals 3 plus the square root of 13 over 2, or x equals 3 minus the square root of 13 over 2 are my final roots. And like I said, they are not pretty at all. So just zooming out here, if I wanted to completely factor this polynomial, I would get, I need to remember the other roots, x minus -1 times x minus 4 times, and here comes the ugly one, x minus parenthesis 3 plus the square root of 13 over 2, and then x minus 3 minus the square root of 13 over 2 in parentheses. So just to clean everything up, x plus 1, x minus 4, x minus 3 over 2 minus the square root of 13 over 2 and x minus 3 over 2 plus the square root of 13 over 2. Whew, they are not pretty at all. Now, the last thing I'm going to do is just verify it with you, just so you know that this is exactly what we're talking about. And the answers that I gave here, so let me highlight what I'm talking about here and here. These are what we call exact answers. Now, the reason why I'm going over this is because the last exam, many of us were using decimals, and you can't use decimals. We want exact answers. So these, all right, are exact. However, if you were to graph this in Desmos, let me show you. So I need to fix everything here on Desmos here. So give me 1 second. Okay, I'm back. But going back into our notes here, 3 plus the square root of 13 over 2, just using a calculator. So back onto this. All right, so here in red, I just boxed in, there's our factored polynomial. We know the zeros are -1, 4, and then -3 over 2 minus the square root of 13 over 2, and -3 plus the square root of 13 over 2. And those numbers are decimal approximations on Desmos. So I'm going to know if you are using some website or something like that, because you're going to get decimal answers using a website. You gotta use the exact answers, or else you're gonna get every single question wrong, even though you're doing it correctly, okay? So make sure you take your time and you just simplify accordingly. That's gonna be it for this video. In the next one, I'm gonna talk about Descartes' rule of signs. Very, very short, 5 to 10 minute video, and that's it. So good luck. This was all about the rational zero theorem, using synthetic division for finding multiplicities if you can, and then writing out completely factored polynomials. If you have any questions, let me know. I'll see you in the next one. Bye.